Hello everyone. Thanks for listening to my presentation of the paper titled "Visual Matching is Enough for Syntax Retrieval." My name is Li Dongwen from Zhejiang University, and the other three co-authors are Yinrong Wang, Dongxiang Zhang, and Gang Chen. Just as the title implies, in this paper, we studied the syntax retrieval problem by focusing on the visual side. Syntax retrieval is a research topic that goes beyond common syntax understanding problems, whose objective is to search and localize all the images that contain the query text. This picture shows an example of a syntax retrieval task. The input query consists of the textual keyword pizza. Given an image gallery, we intend to retrieve all the images that contains test instance of pizza, which are enclosed in bounding box in this picture. Well, such a task is quite useful in many applications, including the product image retrieval, fine-grained image classification, and keyframe extraction with movie subtitles. The motivation behind this paper is that the visual similarity among the images of the same word is quite obvious, as we can see in this figure. Similarity in structures due to the same character arrangement is consistent in style, and maintain consistency is after the rotation. To perform the syntax retrieval task, the first problem encountered is that the query text and images are in two different modalities. To close the modality gap between the query text and the textual images, existing solutions choose to either adopt text detection and recognition techniques to convert the images into text representation or map the query text and text regions into a common Latin space. You can roughly divide the existing works into four categories: the text retrieval method, the word coding method, the cross-model embedding method, and our image-to-image matching method. The text retrieval method reduces this cross-model problem into traditional text retrieval with help of text recognition. They first spot all the text instances in the images and convert them into the correct text strings, then perform the text retrieval among the spotted texts. However, the performance heavily depends on the quality of the underlying recognition model, which may result in inferior performance in the wild environment. The word coding method devises a common handcrafted representation for the word images and the text strings using the PHOC or DCTOW. Then by measuring the similarity in these handcraft features to perform the retrieval, but the performance is still limited due to the discrepancy between the distance of the encoded feature in the common space and the true text added distance. To address the issue of word coding method, the cross-model embedding method uses a learnable feature representation and uses the added distance between the query text and the ground truth text contained in the images to supervise the learning process of common space embedding. In particular, if the query text matches the images, the learned feature in common space should be similar too. In this paper, we make the first attempt to reduce the cross-model syntax retrieval into a visual matching task within a singular modality. Here is an overview of our model's architecture. The model consists of four parts: a glyph resolve visual embedding, a style agnostic feature extraction, a label-guided feature recertification, and a level-based similarity measurement. These models are jointly trained in an end-to-end manner, and the parameters of automation involves of three losses. The detection loss measures the detected candidates value with the ground truth, and the recertification loss measures how the syntax feature is aligned. The matching loss measures the difference between the feature-wise consigned distance and the text-wise added distance. In the first model, the query text is first rendered into an image representation. Given the query word y, the conversion is done alphabetically. A completed word feature consists of individual character features, which are extracted by the ResNet backbone. And the And the textual error in the syntax images is located by the detection module, and we use the FCOS as the test detector, which is trained to detect the text that appeared in the image correctly. Sorry. After the detection, the text instance features is further defined with the instance normalization, which removes instance-specific information from the content images in the scenario, and in this scenario, the tester information. Now, we have the curl test feature and the textual image feature. Before the matching operation, we further define the syntax feature to eliminate the influence of various syntax design and the background noise by aligning with the synthetic query images, which are finely arranged in layout and lucidly in appearance. The refinement process uses feature-level certification to make the syntax image have a similar feature with the representation as the label images. And the final matching is performed by calculating the consign distance among the queries and the local test areas. And the Levenstein added distance of corresponding test pairs is used as a supervision information at the training stage so as to produce more semantic interpretable results. We observe that the similarity learning task suffer from the imbalanced distribution in the similarity space, as most random word pairs are dissimilar. As shown in the figure A, for query words, the proportion of word pairs with low similarity is much larger than those with high similarities. As a result, the learned network tends to distinguish dissimilar word pairs, but difficult to handle the similar word pairs. To alleviate this effect, we use the same word augmentation strategies as one's paper, referenced in the below title. This paper titled "Syntax Retrieval Joint Text Detection and Similarity Learning." This strategy randomly generates pseudo words that are very similar to the given query words. Then both the original query words and the pseudo words are fed into the network during the training process. With such an augmentation strategy, the proportion of word pairs with high similarity is greatly enlarged, which is the problem brought by the uneven similarity distribution. There are 4 types of character edited operation. For example, inserting a random character behind the current character, deleting the current character, or replacing the current character with a random one, and the last one keeps the current character unchanged. We use multiple datasets to verify the effectiveness of our method, including 3 English datasets, SVT, STR, and total text, and 1 Chinese dataset, CSVTR, and 1 multilingual dataset, MLT. Experimental results shows that our method can achieve a state-of-the-art result in commonly used syntax retrieval datasets. And here is a simple visual comparison with the previous state-of-the-art method, where querying with words welcome, fresh, and Francisco. Our method can return the correct result with the bounding box. The effectiveness of our method on Chinese dataset and the multilingual dataset is also demonstrated in the experiments, and since our retrieval process depends on visual similarity, given a different alphabet at the testing stage, our proposed framework can still achieve a decent result with those unfamiliar characters in a zero-shot manner. We reduce the dimension of the representation of the query and the candidates using our method and the cross-model embedding method, and visualize them using the TSNE in this figure. Node labeled with different colors represent the positive samples for different queries, which are specifically marked as stars. The green node left are those negative samples. A circle centered in a star indicates an approximate scope where the majority of positive samples can be covered, whose radius is equal to the distance of the second most distant positive samples from the center. We'll observe that nearly all the positive samples are closest one against the query, with a few green nodes scattering in the circle. This demonstrates that our method's effectiveness is in learning high-quality representation. In addition, the radius of the circle for a certain query in our model is much smaller than the counterpart in the baseline model, once again validating the superiority of our proposed framework. However, there still exists some drawbacks to our model despite the fair results it obtains. Visual matching applied in our framework relies heavily on the pixel level similarity, leading to the problem that some normal objects with misleading shapes similar to the query text will be incorrectly identified as a retrieval answer. For example, the neatly arranged windows and the bricks are usually matched to the query containing the character M, N, or B, and the bicycles with V-shaped structure are likely to be treated as a text. But this limitation is sometimes a blessing in some scenario where some characters are specifically designed as character-like graphics, and our model can still does well in this scenario. Thanks. That's all.